One day in the future, we will have a permanently inhabited station on the moon, and maybe Mars and other asteroids and places like that. But the question is, how do you protect people on the moon from the dangerous environment, the radiation, the temperature changes, the complete lack of atmosphere? And people have proposed various ideas about building inflatable structures, about digging into the regolith, or even various metal structures that would work. But my guest today has been thinking about, could you blow glass on the moon? And in fact, it's such a compelling idea that he has won a recent NIAC award to investigate it more deeply. So my guest is Dr. Martin Bermudez. He is the CEO of Skyports, and they are proposing to blow glass in space, both on the surface of the moon, on the surface of Mars, even in the weightlessness of space itself. And there's a lot of really interesting advantages that you could get from using regolith to blow glass. You could create multiple shells, you could have various atmospheres in between them, and you could provide pressure for astronauts as well as protection from radiation and other advantages to this. And yet it feels so science fiction, and yet it won a NIAC grant. And so they're going to be investigating it further. All right. If this idea intrigues you, enjoy this interview with Dr. Martin Bermudez. Martin, can you walk us through what it would be like to blow glass in the lunar environment compared to what it's like to blow glass on Earth?
Right. Thank you for asking that question. Yeah, that's in everybody's mind lately when people that I've been talking to, and how difficult could it be? And because how difficult is here on Earth, it requires a lot of effort, from the team members. Some of them, hold the blowing pipe. Some of them hold the glasses because it's too heavy, right? So, but in the lunar or any low environment, gravity environment, is pretty feasible. So we've been doing some studies and some type of tests. And it should work. I don't see why not. But you just never know. The physics are crazy. The chemistry is crazy. So yeah, we're trying to figure it out right now. But it looks like we could have a good chance.
Right. I mean, specifically, what are some of these factors that you're looking at? So for example, like the regolith. How does the composition of lunar regolith compare to the composition of the kinds of, I guess, quartz material that you want to use to blow glass?
Yeah, looking at the moon and well, let me go back. The idea was can this be blown up on the moon or any other planet? And thinking about, looking at, all right, so what is the composition of the regolith on the moon? So we look at, it says, wait a minute. So this is almost 40 to 50% in some areas. In some areas, you're talking about probably 80% on the highlands and also on the Mare areas. So, all type of glasses, but they're all glasses. There's a different forms, different materials. So we thought if we have that composition of glass on the moon, so it's feasible. It's feasible to do it. We just need the way how to blow it, because usually here on Earth, you use a blowpipe and, you melt the actual material. In the material, you can have silicates. You can have, for example, soda lime glass, right? Because just aluminum and nitrogen and oxygen, which is just regular glass that we use here on Earth, So, and we think that on the moon, we could have more than we've been asking for. We got the aluminum, we got all of the minerals the ilmenites from the Mare area. We got the anorthites from the highlands, and they're pretty rich in silicates and glass and quartz. So, looking at the composition of the moon about glass, I think it's possible. There is a lot of resources which they need to be mined. It needs to be purified, and that's one question that the NIAC was asking us at the beginning. That it kind of have any impurities. That's how you could. Do you need really the perfect glass? But eventually, we've been going through the process of we might not need the perfect glass mixture, but any impurities is actually going to help.
Right. And I know there's things like titanium and iron and, as you say, aluminum and a lot of this. So the raw material, there may be some kind of purification. I guess this is the point of the NIAC grant is to figure out how do you take what is the raw regolith, the stuff that's the powder that's sitting there on the surface of the moon, and turn that into something that then is the ideal material to actually try and start doing glass blowing. But then the second thing, as you mentioned, here on Earth, when we blow glass, you have a tube and you blow into it, and then you're creating this bubble of air that then the glass is pushing outward with that. And so the gas, how do you think that would work?
Yeah, we started looking at some of the type of gases that we can use. We actually don't want to use air, definitely. Don't want to use helium because it's too thin. I mean, you need something that it needs to actually push the bubble as it grows on the moon, right? Because, I mean, you have a 1/6 gravity. You don't have too much air pressure in it. So basically what we're trying to do is just to mold the sphere of this bubble as it grows. So the gas is a crucial element here. We're looking at argon gas. Yeah, argon gas is it has a lot of thermal properties, and it's heavier than helium in air. So it's a noble gas. It's not combustible because when you get this gather or this melting material, right, it's pretty hot. It's extremely hot, so you don't want anything to be explosive or anything like that, in there. So, so this argon gas is what we're looking at to do, and it will actually help to actually mold the glass from inside. It will create like internal pressure as it blows out. So eventually, with the equilibrium, it will create a equilibrium pressure from the inside.
Now, again, I'm sort of imagining these reality shows I've watched where people are blowing glass into all kinds of crazy shapes, and you're dealing with the atmospheric pressure of the Earth, which is then pushing back against the air that you're putting in the inside of the glass. And so in the vacuum of space or on the surface of the moon, you don't have that pressure pushing against. Does that help or is that a problem?
No, actually, when we start looking at this at this idea, we thought, okay, wait a minute, how is it going to be doing glass up there, right? So we figured out that low gravity environments, it will actually, this doesn't affect anything. It actually will help. If you notice. But one thing that we're looking at is that as the gas pressure, because it's a pressurized gas that we're injecting, right, inside this melting compound of glass and material. It's not only glass, but we're looking at some type of glass matrix, which might have titanium, it might have aluminum. So that will enrich the glass and it will create some crystals that we don't know yet. And that's part of the study of the NIAC, identify how these mixtures will be affected by gravity and also pressure from the inside. So we're looking at, okay, so should we just blow it by itself and just keep the pressure? And that's pretty intense, how to keep it. But we need to actually rotate the sphere, just like here on Earth. I don't know if you've seen some of the glass blowers, they usually rotate it. So the actual gather of the melting material, it starts taking shape. But I think it's going to help us, Fraser.
Yeah. So and then you sort of brought that in the next point, which is that 1/6 gravity on the surface of the moon. That is going to be trying to make your structure slump back down, and it's not like you can hold it out on a pole and turn, or maybe you can, I don't know, right. While you're rotating it and then later put it. I mean, do you have a sense? Is it a speed issue? Is it just how quickly you get as long as you maintain the pressure inside, it doesn't? How do you sort of deal with that?
Yeah, we've been looking at the speed and the pressure. We know that the compound of the actual glass, it needs to actually be really strong glass, definitely. But then the speed and the slower that you vent and you inject this gas we figured out so far that is the best way to do it. Because then that pressure that we injected into it, right? Because it's not like Earth that we have this air pressure and gravity. We're dealing with a little bit less up there. So try to balance the actual pressure of the gas. And like I said before, to spin it. So somehow create this mold to actually grow and grow and grow. And that had given us some really cool analysis so far that, if we rotate it and if we keep the amount of gas pressure in slow pressure, because you don't want to just go so fast, right? So then we can actually keep the thickness of the glass as it grows. So usually here, blowing glass, you get the North Pole and the South Pole a little bit heavier than the actual equator of a glass sphere, right? On the moon, we're looking at if we do all those steps, we can have all uniform thickness. And that's been one of the questions that the reviewers from NIAC was saying. If we can able to keep the thickness to the overall glass shell, I think we can do great things up there.
And then sort of the last sort of physical question that I have about this is in terms of the radiation. Like, again, here on Earth, you're in a room where you're blowing the glass. You don't really have to concern yourself too much with the light coming from the lights. You don't have to worry about the heat. Like, it's really just the conditions of it itself. But out on the moon, you've got this, if you're in sunlight, then you're getting direct sunlight coming from the sun that is going to be heating up the interior of this. That's going to cause various thermal issues. And if you dare try it at night, then it's incredibly cold. Do you have a sense, like, when is the best time to do this to try and manage the thermal issues?
Oh man, that's a great question. That's what we're trying to figure out. And so far, we figured out that if we use the type of glass, for example, borosilicate glass, aluminum silicate glass, right? You have the actual former of the matrix, which is silicate, but then you add up more of the aluminum, and also you can add titanium, you can add some other one. And now if you can add graphene, which is being found on the lunar Earth, rarely, zirconium could be another one. So that will, if you have that matrix or compound of glass already mixed and melted, so then it will serve most likely if you do the process of melting during the lunar day, right? You're dealing with the high temperatures, but eventually we figured it out so far, and there's still a lot more testing to do. The actual melt, when it comes out outside the furnace, right? You could be around probably 1600 Fahrenheit. I would say around there. But when it comes out, because it's going to come out actually of the furnace, and then when it comes out, it could be about 900 and dropping fast. So timing is really, really, really crucial. So when this heat coming out of the furnace encounters the hotness of the actual lunar surface, because it's pretty hot, it actually figured out that it could actually help in the annealing process or the cooling process. So it won't actually affect it as far as getting too much heat, since it's already generating. It's already hot. So, but the lunar day temperature will actually create a thermal gradient that it will kind of balance that, the coolness of the bubble, but eventually comes out what kind of matrix or compound of what the glass is made of. That is really crucial. Right.
And so let's kind of put it all together then. So we've got some spacecraft or maybe the astronauts on the surface of the moon. This mission flies to the moon, collects up the regolith. Somehow it is sorted out, or it is refined down into the right kind of raw material to do this. How will this process then happen? Like furnace, blowing, timescale? Like if you were an astronaut standing beside the habitat blower, what would you see?
Oh boy, it's a great question. Eventually, we're not doing the mining at all. We're gonna let some other companies to do the mining and just do the collection of the glass. We will identify the actual matrix that we need. So we have this furnace that we're gonna construct here on Earth. Eventually, it's gonna be designed as a holding facility. To put all this already mixed glass matrix or compound. So eventually, when you stand it on the lunar surface and you get these companies who are doing the mining, and we're going to actually fill the actual furnace with the type of glass that we're looking for, because eventually the actual and I guess it's time to show you the little model.
Yeah, I love when people have models that we can see.
Yeah. So right. So basically, this is the lunar surface, right? So this is the actual furnace that is going to get built and designed here on Earth, right? So it has all the blowing pipes, and it has all the furnace area and melting systems in here. So basically, what we're going to do is actually fill this up with whatever compound that we need per each layer. Because eventually we figured out if we only do one shell, it's not going to be sufficient, for thermal properties, because it's really hot. So we kind of thinking like here on Earth, like double glazing windows for buildings. So, and it's interesting because in double glazing windows, you have these two sides of walls, right, which is made of glass, but in the interior they have argon gas, right, which is an insulator. So we thought, okay, well, we can kind of do that on the moon. So basically, what we intend to do is just do the first layer, blow the first one, right, and then do the second layer, right, and so on. And then you see this gap in between, right? So basically, this is gonna be filled out with argon gas just to create this sense of thermal barrier, pretty much. So in insulation. So at the end, you have what we call the nest. This area is supposedly going to be called the used for all the astronauts, the living quarters, pretty much. So this is going to be shield from all the radiation, and the way we thought, okay, now if we can control the actual thermal properties, all the hot, and make it colder inside, we can actually design the interior is pretty cool. So let me show you this. So this is another model of the nest. This is the interior, the living quarters, right? So the living quarters, we're thinking about either making two spheres and filling them up with regolith. Make it 2 meter thick or 3 meters thick, depending, just for radiation purposes. So then, if you see the interior of this, so now this is the living quarters right here. Oops, sorry. So this is what happened. So then the actual interior, this is where you see the how this is going to be helping out with radiation. Then you come up with the actual interior here, and you got your floors, and you got the core. So this becomes the living quarters inside. So it's gonna be pretty protective, pretty much.
Right.
Yeah.
Right. And so, I mean, this seems, I mean, obviously this is purely hypothetical and theoretical and, imagining what, 50 years down the road when people have developed the technology and tested out many times. But this idea, I mean, of glass that would be potentially, like, how thick would this glass be in that sort of final phase? Meters thick?
Great question. We've been looking at possibly not a meter or not a foot. We're looking at probably 5 to 6 inches. Could be a foot. It all is going to depend to a lot of things to line up pretty well. The size of the pipe, that's going to be doing the actual blowing. The thickness of the pipe, actually the actual type of glass matrix too. So we're looking at 3 to 5 inches so far. We're hoping to do some more testing, and if we can get it to probably a foot, and then we're doing really well. we find out also that if we do it thicker, it actually is going to work against us because it will actually take a long time to cool off because it's more thicker. A thinner layer shell, it will be much better. It dissipates heat faster that way.
But I think it's surprising to people to hear that in fact glass doesn't have to be that thick to hold the pressure of the atmosphere in. I mean, was this surprising to you as you started to do the math?
Absolutely, yeah, absolutely, yeah, and we still gotta continue to do a lot of more testing, but it's looking that way. The thinner is better, and actually is in compression and then tension, because if we use borosilicate glass, for example, right? So boron in the matrix will help to actually for thermal shock. Because if you're going to be putting this glass up there and you're going from really hot to really cold at the night, so what's going to happen is this actually this glass, it will thermally will take all this heat and it will be a thermally shock barrier for that too. So there's a lot of properties. So right now we're looking into what kind of mixtures we're going to use. Should we use borosilicate glass? Should we use more boron? So this is just a very fine tuning that we're going to be doing through this study to identify which type of glass we need per each layer. As you go down this kind of onion layer thing, we need to figure out which layer will help better as it goes down into the actual core. Yeah, it's really, really, really interesting. And during the night, it's so cold. It's so unbelievable. Even we find out that even argon gas, pressurized, right, just to keep as shielding and maintain a little this temperature lower. At night, it will solidify. Below 180 something Celsius. So we're going to be looking at adding more weight into that particular area, right? So we're looking into like, whoa, what is argon gas going to be doing during this so lower temperature? So this is, as we go and research more, we're finding some really interesting things. I didn't know that, argon gas will solidify and become a crystal at a so lower temperature. And we're like, oh boy. So we're going to have layer and then thickness of the actual argon gas. And then, so yeah.
But there's a lot of really interesting thinking about how you could use the thermal mass of the moon itself as a way to kind of store heat. There's these interesting sand batteries in Finland where they use solar power to heat up the sand underneath the facility, and then it will last them for like 9 months. They can just keep drawing heat away from it as well. And people have even done these kinds of estimates on the moon that you could say you've got pipes that are installed inside of the network, then you could be during the day when it's 130 Celsius and it's way too hot, you're pulling that heat out of the outer, out of the sphere and parking it into the regolith underneath the ground. And then when you're going through the night phase, then you're drawing that heat back in and using that to warm it up. So, my guess is that you'll be able to, by banking the heat, get through the night. So,
Yeah.
but and then, I think people are probably going to wonder about the strength of this glass for micrometeorites. Are you going to get a hit and the whole thing is just going to shatter if the wrong micrometeor hits?
Yeah.
How strong would this be compared to the other kinds of lunar habitat material that people are considering?
Right. That's one of the actual topics that we're going to be really, really going after, through the NIAC phase 1. And what we already figured it out so far, and again, there's a lot more testing, is that the actual matrix or compound of the glass, if we use graphene, for instance, if we use zirconium or, it's just so many, make it as strong as possible, right? So if we get that strong glass, stronger than steel, then if we say we only have one layer of that, so our idea is just to create more layers, blow more layers, because then we can actually use a concentric pipe unit. So we can say, you know what, let's make this let's use 3 or 4 spheres, right? So we're gonna blow one big one, another one will come out, blow another one, and we can actually time it as the two walls come together, and we can actually say that we could possibly get it closer, maybe a meter, and then we can have another one comes out. So we can create this barrier between 3 to 4 or 5 shells if we need to, just to get this thickness and really, really, really strong, actually, outer wall. The other thing that we're thinking about, okay, if we build this 3 or 4 shells right together with argon gas, if we got a micrometeorite coming in, so we're thinking about also spin the actual outer shell, since one shell is going to be adapted together with one pipe, we can actually turn that sphere on its axis. So by turning it, we're thinking, and this is a lot of study to be done into this area, but if we spin it, if a micrometeorite comes in, since it is a spherical shape, right, it doesn't have the actual flat area where it will absorb the impact. It will actually dissipate the impact, and if we turn it, we don't know yet how fast, then the actual, it will deflect it, so it won't take and absorb the heat as much. So it's still a lot of more testing to do, a lot more modeling, but that's what we're thinking. If we can make a turn and make the wall really thick, not by itself one shell, but many shelves together, so we could have a good results, I hope.
Now, obviously the proposal is thinking about this on the moon, but I'm sure people are wondering, like, what if we did this on Mars? Do you think the same factors would come into play? I mean, heavier gravity, different kind of regolith, more atmosphere concerns?
Yeah, we've been looking at that too, and actually it's going to work. But there's only one place, Fraser, that we can do this, is at the top of Mount Olympus.
Oh, really?
Yeah. Because of so many things that we look at. We haven't, gone into too much, but we think, okay, if we go up that high, since it's a very thin atmosphere, there's not too much wind up there. Might be some winds, might be not. So you're really high from the surface. So if we can actually bring the furnace up there, and actually at the top of Mount Olympus, we find out that, through research, that there is some type of glass that we could use. Got like feldspar glass. We got olivine too up there. There's so many minerals that we can use. So the actual thinner the atmosphere could help. The high of the mountain could help, because we don't need that much of pressure, right? So at that high, I think it's a good possibility. And we got, the glass might not be the same as the moon, but they still have some really good glass. Like olivine is pretty strong glass. We can get it from there too. So we don't know yet what else Mars has, but I'm pretty sure that they have. I mean, all those domes that you see are there, and I'm thinking, every time I see domes of sand, I'm thinking, wait a minute, I hope there's some aluminum, they have some titanium in there. But yeah.
Yeah, I mean, that's the thing. Like, when we think about domes, when we think about Mars habitats, we're thinking about these domes. We're thinking about these curved domes. Like, how do you get a curved dome? You blew it the way you blow glass. So now what about just like the weightlessness in space? So let's say you are mining material off of the surface of the moon. You're getting just the right mix. You're refining it, and then you're sending that to space. What about blowing these things in weightlessness? That feels like it takes away even more of your problems.
Actually, when I started speaking to the NIAC people, they say, this could easily work on microgravity. And you don't have nothing up there. You just blow it, right? No restriction on atmosphere, no nothing, no pressure, no nothing. So the only thing that we could encounter is weightlessness. So we probably will need to adjust the furnace. So, on the moon or Mars, you have this little pressure that it will hold together the melt inside the furnace, right? So the tighter that you hold it, the easier it will be for the pipe to gather on the nozzle and then extrude it and blow it. In microgravity, the actual melt could be moving, or it could be hard to do to actually stick into the actual blowpipe. So we've been thinking about it's doable to do some, most likely have a very tight compartment inside the furnace, so we don't have this melt going around and shoveling around, so it won't gather too much on the nozzle to blow it. Other thing that we can use lasers also to actually burn the melt. So it has a great potential in microgravity, better than the moon or Mars. But it all comes out to the pressure of gas. Eventually, that's what we figured out. We're looking at how big can this thing get, and that's scary. We don't know. It could grow. It could grow miles. Interesting. I mean, I'm still not believing this idea. I believe it, but I'm thinking, oh boy, how big can this thing get? And one method that we could use in microgravity, it could be that we could have, let's say, 200 pounds of melt, right? Not too much. Then we can have the pipe extruded and then blow it, right? So it's like blowing a bubble gum. You still have some residue of the bubble of the gum while you building this sphere or this bubble. How we can feed it more as it grows. So we're looking at also at that technology. How if you get this gather and the pipe gets this much, but we still have some more melt that we could use. So how we can compact it and bringing it up to keep feeding it. Feeding it. So,
but it's interesting. Like, there's a kind of telescope called a spherical telescope, which is essentially a hemisphere that is mirrored, and then it focuses the light, and you have a telescope. And many telescopes are just, some are parabolic telescopes, and others are these spherical telescopes. And so I can imagine that you could blow the bubble in space to whatever size it is possible, and then you wait for it to cool, and then you could like slice it in some angle, and then you mirror one side of it, and now you have this gigantic, sort of mathematically perfect hemisphere that is a spherical telescope. So not just habitats, but it feels like there's a lot of other really interesting applications for using this kind of technology. So I want to shift gears, Martin, because I think, you have been working on this idea for several years, and you had a really interesting experience in working with the NASA NIAC group. I mean, you got your award this year, but this isn't the first year that you applied. And so I think for a lot of people, they see just the outcome, but from your experience, what was it like to kind of go through this from when you first were like, okay, I'm going to try submitting to the point where you actually won an award? What was that like?
It's perseverance. Perseverance. If you believe in your idea and you think that this idea could change the world, and it could change many things. In my case, my personal case, I thought like, well, I'm an architect, and I thought, okay, how can my knowledge can be used up in space, and everything is just, just looking at pretty good. Space is like coming along so fast. How can I use all my knowledge? So when I started applying to NIAC, I thought, oh man, this is hard. This is gonna be hard. Especially this, you gotta read, you gotta, do a lot of things. But again, I said, if you believe in yourself and you believe that your idea can make a difference, you go for it. And at the beginning, the first time, they really, I got a yellow color, which is, this is how the way that they do it. You got black, you got red, and you got yellow, green, and I think blue. So if you black and red, means that the idea doesn't work. You need to redefine it, make it. I got a color yellow, which is a pass. But eventually I find out that I guess it was more like a few questions from the review panel. What is this? Like the thickness of the shell was one of the questions. How can the bubble that is going to collapse? How might not collapse? So I took that time to really come back and reflect and say, okay, well, I think I got a yellow color, which is passing, but it needs to be refined a little bit. So here we go again, try it again, fix it up and submit it again. And eventually it worked. They really liked the idea, Fraser. They really loved the idea.
Yeah. I mean, we talked, you and I first talked, it feels like 3 years ago, maybe.
I think about 2.5.
2.5 years ago. Yeah. Yeah. And you had, you were developing this idea then. And so you went through the review process twice, or was this your third?
Twice. Yeah. Well, the first time that I applied, I got a yellow color, which is pass, but there's still some question that I need to answer to make it happen. So then I applied again this one and answered some of those questions. So I would say twice. Yeah.
Yeah.
So,
right.
Yeah.
And that process of having this really good detailed feedback by knowledgeable people who are kind of excited about what you're doing, but also need to be convinced. Did you find that by going through that process, you learned quite a lot and were able to make a better idea?
Yeah. No, definitely. They're pretty helpful. The NIAC team is pretty helpful. Dr. Ron Turner, he's an amazing guy. I get in touch with him and say, hey, what do I need to do? This is a pretty good idea. But he said, well, you need to do what the review asked him for. And if you do that, you have a good chance. This is what we've been looking for, ideas like this. They're really far ahead, but there's still a chance that it could be feasible. Still a long way to go, a lot of more work. But I'm thinking that, like I said again, if you feel like your idea is really burning in your chest, and you want to get it out, and you find that little light at the end of the tunnel that says that could be possible. So applying for the first time, it gave me that little light at the end of the tunnel. And I said, well, it's not all darkness. So if I go a little bit further, I will get it. And it's pretty exciting, So I really think the NIAC team, they're pretty professional. They're pretty helpful. They help in any way. When I had questions, I emailed them right away. When you apply, you get these forms you need to fill up. You need to comply with everything. So my first time, I thought, oh boy, I'm gonna do that. This is my first time, but asking questions, and they're pretty good at that. They're pretty awesome.
And I really feel like your story should be a real inspiration for other people who have ideas where you may have expertise. As you said, you're an architect, right? Not a roboticist, not an astronomer, not someone who has worked on various missions or habitats or any of that in the past. You just have this very specific knowledge with a kind of a twist that you have this knowledge with blowing glass as well, and as it relates to architecture. And that you can go, well, does this have an application to space? And it turns out that either people never really asked the question or never took the right level of expertise to ask the question in a way that could give you any kind of meaningful outcome. And so they were waiting for someone to come and provide solutions and ideas like this. And it's funny because I talk to people who won NIAC awards, and they also will get rejected because their idea isn't weird and futuristic and out of the box enough. It's too normal. And so I think that for a lot of the people out there, when they have an out of the box idea, they have a very specific kind of experience and knowledge, and then they say, but is this, does what I know about Earth relate to space? Maybe. And that it's this process of like going through this system to formalize your ideas, to put them together in a way where you are applying this to space, and that people who do know about space can ask you pointed questions and try to make you fine tune your idea. And then out comes something that in fact someone wants to investigate it as it relates to space. And so I find this so inspiring. And we've been talking for years, and I've watched kind of every step of this process as you've been going through this. And so I'm so excited that we can talk about it and present it here in this format with you winning the award. And then hopefully we'll have this bold future of habitats on the moon and in space, which are like the sci-fi future we were promised, where you're living in these spheres and you're seeing out across the lunar landscape. That would be awesome. So Martin, what are you obsessed with right now?
Oh boy. I'm a big fan of Gerard O'Neill, and also Dyson Freeman, and Freeman Dyson, sorry. And I think the vision was way ahead of their time. I feel like if I can contribute, and this technology could become something that it could be help humanity, it could be help Earth, to build these habitats made out of glass, really strong glass, really with atmospheres inside, people living up there. I think I will accomplish what I feel in my mind, that visionaries are how can I say, really interesting, depending on the time. And if this idea was put in my head somehow, so to accomplish that idea for us to move out of this Earth and help humanity be interplanetary and build these glass domes, these glass spheres, and eventually, not just create these spheres, but telescopes. It's all range of things that I've been just looking at, and I'm thinking, okay, well, one thing could be that if we can be able to blow this sphere, right, you can be able to blow actually an energy sphere, silicon. You can blow silicon in space, so you can have, instead of the flat solar panel, you can have a spherical solar panel, miles in diameter. So that can be sent, to become, Dyson Swarm. So it just so much that I can think of. If I know it's gonna be hard, I know it's extremely difficult. I'm hoping to, as I get to the NIAC and NASA, I will have more access to resources, testing facilities, and scientists. So learn more about the technology, and hopefully build these habitats. I feel like this is the time.
Yeah,
this is the time, Fraser.
Oh, it's great. It's great. Awesome. Well, congratulations, and I look forward to your final report.
Thank you so much, Fraser. I appreciate it.
I hope you enjoyed that interview with Dr. Martin Bermudez. Now I'm going to give you some additional thoughts, but first I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Gilton, and David Matz, Dennis Silberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Robach, Sean Sargent, Spiderswap.io, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. In addition to just this amazing idea of being able to have blown glass habitats in space, and when you see the various mock-ups and renditions, it looks cool. Like that looks like that science fiction future that we've all been hoping for. But I want to kind of double down on the mini rant that I did in the middle of this episode, which is that I think a lot of people are waiting for others to come up with the ideas, to figure out the practical ideas for solving problems in space. But what we have found time and time again is that innovation comes from knowledge and experience, often in unrelated areas. And yet people are waiting. They haven't thought of the idea, the out-of-the-box idea that can then solve a bunch of these problems. And so you might have experience in something that is completely unrelated, and yet the problems that you have to solve actually directly relate to the problems that we're going to be solving as we go to space. Because when we go to space, we have to do everything that we do here on Earth and more in terms of heating ourselves, cooling ourselves, providing oxygen, water, food, and then all of the various material sciences, but they're made more complicated. And so certain kinds of ideas will help solve those problems. And so if you have knowledge, if you have good ideas, if you're inspired, then there's some really interesting outlets that you can use to actually try and see ways to make your ideas become practical reality and solve the challenges that humanity needs to become an interplanetary civilization. All right, we'll see you next time.